Hello everyone, welcome to the first lecture in the course Theory of Computation. In this lecture, I will be giving you an introduction to the course Theory of Computation, where we shall see what this course is all about, what can we study from this course, and what this course has to offer. Alright, so let's get started. So what is Theory of Computation? This theory of computation is one of the most fundamental courses of computer science. This course is one of the most fundamental as well as abstract courses of computer science which every computer scientist and engineers must know. This course is not going to help you write programs or build a computer as such, but it will help you understand how people have thought about computer science as a science in the past 50 years. Okay. So what does this mean and what is it really about? So this subject is mainly about what kind of things can you really compute mechanically, how fast can you do it, and how much space does it take to do so. Okay, so we know that in computer science there are certain kind of problems that a computer or a machine can solve. And also there are certain kind of problems or things that a machine cannot do, or certain kind of things that a computer cannot solve. So we shall be seeing all these kind of things in this subject. Okay, so we talked about how fast and how much space does it take to do so. So let us just leave these 2 points for a while and let us just focus on about what kind of things can you really compute mechanically. So to make this point clear, let us take a simple example. So let's say I want to design a machine that accepts all binary strings that end in 0. I want to design a machine that accepts all binary strings that end in 0. So my machine that I design should accept all binary strings that end in 0 and should reject all other strings that does not end in 0. Okay, so let me take an example string here. Let's say 110101110. So this is my example string that I have here. Okay, now what I want to do is I should check whether this string is accepted by my machine. So as a human being, how would I perform this task? As a human being, I would just look at the last digit, and if I see that it is 0, I say yes, I accept it. Or if I find that it is equal to 1, I say no, I reject it. So how would a machine do this? A machine would scan the last digit, and if it finds that it is equal to 0, it says yes, it is accepted. Or if it finds that it is equal to 1, it says no and it rejects it. Why? Because our machine is supposed to accept all binary strings that end in 0. Okay, so that was fairly a very simple example. Now let us take another example. In this example, I want to design a machine that accepts all valid Java code. It accepts all valid Java codes. Okay, so what should my machine do? My machine should check the binary equivalent of my codes. When I write a code in Java, it should check the binary equivalent of these codes, and from this binary equivalent it should tell whether this came from a valid piece of Java code or it is invalid. Okay, so my question is it possible to design this kind of a system? The answer to this is absolutely yes, we can. And the best example I can give for this is compilers. When we write a piece of code into our compilers, let's say that I'm writing a piece of Java code. So I write a piece of Java code into my compiler, and when I compile that program, if I have written that program correctly without any mistakes, the compiler compiles that program and runs it because it is valid. On the other hand, if you have made some mistakes in that code, or if you have written something wrongly, then the compiler tells you that there is an error and it does not run the program because it is invalid. Alright, so we see that it is very much possible to design this kind of a system. And from this example, I think we got a slight hint that the whole of compiler design it came from this subject, Theory of Computation. Okay, so I hope that was clear. Now let's take another example. Now in this example I want to design another system that accepts all valid Java codes and never goes into infinite loop. I assume you know what is the meaning of infinite loop. Okay, so I want a machine that accepts all valid Java codes and does not go into infinite loop. So is it possible to design this kind of a system? So from this previous example, we have found that it is possible to design a system that accepts all valid Java codes. This part is possible, it's fine. But we have one more condition here, and never goes into infinite loop. Can I design a system that never allows my code to go into an infinite loop? The answer to this is no. I can never design a system that performs this task. Okay? So even if you design it, you would either get the wrong output or it could run forever and give you no output at all. So this kind of a machine that performs this kind of a task cannot be designed. Okay, so this third example has given us an idea about what kind of things can we not compute mechanically. Okay, I hope that was clear. So what is this subject all about? In this subject, what we usually do is that we have a system or a machine. We design a machine, and suppose this is a machine, and then we send an input to this machine, and then the machine thinks about this input based on some formula or based on some rules, and it either says yes and it accepts the input or it rejects the input. So this is what we are going to basically do in this subject. We are going to design systems or machines which can take certain kind of inputs, and this machine will be based on some rules, and it should either accept the input or reject the input. So this will be the thing that we will be doing. Don't worry even if it is a little unclear right now. When we take other examples and when we start from the very basics from the following lectures, it will all become very clear. Okay, now let us see what are the layers or the levels in this subject that we have to go through. For that, I will show you a diagram over here. So here I have a small diagram showing the layers or levels in this subject. So in the first layer we have FSM. So what is FSM? FSM stands for Finite State Machine. FSM stands for Finite State Machine. This FSM, that is Finite State Machine, it is one of the simplest model of computation. It is the simplest model of computation, and it has a very limited amount of memory, and it can perform very low level computations and calculations. Okay, this is the basic building block of this subject. This is the first thing that we will be learning. So keep in mind FSM, we'll be starting with it in the following lectures from the very basics. So don't worry even if you don't understand these terms now. We will make it clear as we go further. And then the next layer we have is CFL. CFL stands for Context Free Language. Context Free Language. CFL stands for Context Free Language. And CFL is a little more powerful than FSM, and it can perform some more higher level of computations as compared to finite state machines. Okay, and one thing to remember here, this language over here, this language here does not mean a programming language. Okay, when we in computer science, when we come across the term language, we often think, oh, this means a programming language. But no, in this subject here, in this context free language, this language actually means a set of strings. a set of strings is what is known as language. It will become clear when we explain it further in the following lectures, so don't worry about it. And in the next layer we have something known as Turing machine. Turing machine is a machine that can perform high-level computations and calculations. It was designed by Alan Turing in 1940, and it is much more powerful as compared to context-free language and finite state machines. Okay, and in the next layer we have this undecidable. This is labeled as undecidable, and why is that? It is because the problems that cannot be solved mechanically, those kind of problems, it falls under this undecidable layer. Like for example, above some time back we saw an example about a problem that could not be solved mechanically. So those kind of problems that fall, they fall under this undecidable layer. Okay, so these are the layers that we have to go through, and we will be starting with finite state machines, FSM, in the next following lectures. So we'll be start with the very basics. So don't worry, even if you don't understand these terms that we used here, it will become very clear as we start from the very basics from the next lecture onward.